Good afternoon, everyone.
It's my great pleasure to welcome you to today's ISSAI guest lecture. It's my great honor to introduce our distinguished speaker, Dr. Amr El Abbadi, Professor of Computer Science at the University of California, Santa Barbara. Professor El Abbadi is a globally recognized leader in the fields of distributed systems, databases, and cloud data management. Over the years, Professor El Abbadi has been recognized with some of the greatest achievements of our fields. He is a fellow of the ACM, the American Association for the Advancement of Science, and a fellow of IEEE, reflecting his significant contributions to both theory and practice. I hope some of you in your careers will achieve some of those recognitions as well. He has also held important leadership roles, including serving as the chair of the Computer Science Department of the UC Santa Barbara and as Associate Graduate Dean. In addition to his research and leadership, Professor El Abbadi has made substantial service contributions, including serving as the editor of the leading journal, the VLDB Journal, and IEEE Transactions on Computers, to which we are sending once in a while papers as well, and as the program chair of major conferences, including SIGMOD. Today, Professor El Abbadi will present his talk titled Taming Big Data, Stream Summarization and its Many Applications, which you will enjoy a lot. In this talk, he will explore how advanced mathematical techniques can be utilized to efficiently extract meaningful insights from massive, continuously generated streams of data. This topic is extremely important in the days of big data and artificial intelligence, and I hope it will also contribute to your research efforts. Please join me in warmly welcoming Professor Amr El Abbadi. Thank you, sir. It's an honor.
Thank you. Good afternoon, and thank you for inviting me. It's really a pleasure to come here to Astana and Kazakhstan in general. I was a week in Almaty and I had a great time. Can everybody hear me clearly in the back? Okay. So what I'm going to be talking about today is mainly about data streaming. So it's a problem that is almost the reverse of what a database does. In a database context or a data management context, you have data and you have queries that are coming in, and you want to answer the queries continuously. In a data stream, you have the queries sitting and the data stream coming in packets. So you can think of it as in a network, for example, you have packages and you are interested in what are the top IP addresses that are being sent. So it's basically a data analysis type of problem where the data is flowing very quickly and the queries are typically fairly static. I'm going to start with some historical background, some work not of mine, and then some work of ours that me and my students have been doing, and there are listed several students' names here, and Professor Digvi Agrawal, who is my colleague, and we work together on many of these projects. I'd like this talk to be interactive, so if there's something you don't understand or don't follow, just don't hesitate to ask me. It will be easier to clarify things. And at any rate, the talk is fairly modular, so if you lose me at some point, you'll probably can catch up again later on. So this is kind of a dated slide, but it shows you approximately what happens every minute on a large scale and this is about a year ago. So you can look at it and say there are 231 million emails that are being sent every minute. There are 6.3 million Google searches. All of these things are happening rapidly. You're sending requests, you're doing likes on Instagram, you're doing all kinds of things that are continuously, and somebody is trying to analyze all of this stuff. Yeah, so that's the context in which we're working. So big data has a lot of applications, and here I'm in a data center environment. So you are all familiar with various activities, whether it goes from e-commerce to meteorological, astronomical data that is being beamed continuously, to just regular human activity. For example, you are familiar with Fitbit or these devices that you wear and it keeps track of your heartbeat and all these kind of things. All of this data is being generated and sent out to basically data centers and places where they have to be processed. So I want you to look at this picture and don't worry about the details, but what's important is the slide has two graphs, one on the left and one on the right. The left shows you the growth of the data that we are generating, where the x-axis is time, so 2010 to 2025, and the y-axis is the amount of data that is being generated. First observation, it's exponentially growing, and two, the peak is about 175 zettabytes. It's a huge, big number, 10 to the 18 or something. Compare this with the graph on your right, which is also x-axis is time, y is growth in terms of size, but it is the amount of storage that we are generating, the storage that can store the data that is being generated there. Now, the peak of it is about 22 zettabytes. So there's a significant difference between the amount of data that we are generating and the amount of storage that we are generating to store this data. So obviously we cannot store everything that is being generated. There's just too much of it, and most of it, maybe we are not interested in it. So in general, the data is large and growing, and what we are going to try and do in this talk, and I'm going to focus on very specific problems, is to extract patterns, to extract trends, specific descriptions, particular properties. That's the kind of thing that we are trying to do. So in general, you are trying to create some data object that summarizes the data. And it depends on what you are interested in that we are going to summarize. Data summaries basically dispose of many details that we might not be interested in. Unfortunately, for every property that you are interested in, and I'll show you different properties, there are different summaries, including most of our work, except for one at the very end. So the question that still remains for PhD students and researchers is, can we start to explore one or two specific summaries that might be multi-purpose, that might be applicable for more than one thing? We just have one example where this seems to have worked. So let me start with some warm-up. So like when you do an exercise, you try to warm up. So here, this is just to get you warmed up. So take your favorite company, big company, and let's assume it's structured in a hierarchical manner. So there's the top administration, but then it has several components, mail, YouTube, and YouTube itself has multiple aspects, some of it dealing with music, some of it specifically YouTube. And each of them is generating revenue. Yeah, each of them has its own revenue. So if I know the leaves have revenue X, Y, and Z $million, then can I ask, what is the revenue of the entire company? That should be an easy question. All you have to do is add them up. I'm not asking difficult questions, so don't be scared. So that's a summary. At this point, we are summarizing the revenue of all the leaves in one integer, actually. So one integer captures one interesting summary, and I can keep on doing this, yeah? So summarization is easy if it is just addition. If it is, in this case, the total revenue. Are you all with me? I just need to get some visual reaction. Now let me change the problem a little bit and make it a little bit more interesting. I'm interested in unique visitors to Google in general. Now, there are people coming to different places, and often there are repeated people. I go both to YouTube and to music, and maybe I use their email. So let's assume we are going to color, for this example, the people. So we have the red coming here twice, the blue once, the purple once, but the red is also coming here and the red is also coming here. Now I ask you, what is the unique number of visitors that come to YouTube? It's not as obvious a question. It's not like the revenue. So I'd like to be able to answer the sum is only 4 out of all of this. So each of them accumulates information. Now just one number is not going to be enough. If I give him only 4 from here, you don't know how many read and how many. And in general, there can be lots of different people. Think of these as IP addresses. I can't keep all the counters of all the IP addresses. I could, but I don't want to do that, yeah? So, and so on. So, and I can not only ask about daily, I can ask weekly, and I can complicate things as much as I want. So even the simple question of uniqueness versus just counting addition makes us think. We have to come up with new solutions. This type of problem has lots of applications. Even the unique one comes up in database optimization query a lot. You're estimating cardinality. Network monitoring comes up as a very important application, actually, for a lot of this summarization work. And a lot of our work, although I come from a database background, and most of the work is published in database conferences, actually, it's the networking people who have benefited more, I think, from our work. So just to show you, you work on something and then in the future somebody else benefits from it, which is the beauty of research. Most interestingly now, there's a lot of interest in these summarizations. Often they're called sketches, if you're familiar with this. Like in federated learning, this comes up where you want to hide information, you want to send only a sketch of information. So now, recently we had a paper in Europe's conference because we were just doing something in a private way that we on sketches. So there is interest in all of this stuff. An important one that drove our research initially was online advertisement. And I'll come to this when I present our work. So kind of the structure of the talk is going to be, I'll first give you, since I started with this distinct count or unique visitors, I'll give you the solution, which was 40 years ago. So this is old stuff, but it's really interesting to understand it. And then I'll delve into the frequent elements, which is what we have worked on a fair amount in the last 20 years. And then, depending on the time and the professor here, whether I have 2 applications, and we can decide whether I want to do caching or I want to do a networking application. Okay? So that's the structure for the next 45 minutes. This clock is off, by the way. Yeah. I also work on clock synchronization, and clocks disturb me. Okay, so let's go back to the unique visitors problem. So let's assume that every visitor has an ID, and the ID is represented using 64 bits. So which means that you can have 2 to the 64 visitors, potentially. That's the size of the universe. Obviously, we are not going to get 2 to the 64, but we don't know where in all of this we are going to work. So it's a very huge domain. The domain is big. The actual visitors are going to be much less, or the unique visitors are going to be much less. The question is, who do I keep track of? And so you have visitors like this coming, and the simplest solution, if I give this to somebody in 101 computer science, they would say, well, build an array and keep track of everybody. And once you've seen somebody once, you don't count them again. So that's a trivial solution. It requires 2 to the 64 elements, bits, that's a lot. It's a bit array, and every time a visitor comes, you set the bit, initially it's all zeros, and then when a visitor comes, you set it to 1. And then it's stuck there. Given this, if I ask you now, I stop here and I say, how many unique visitors have you gotten? What would you answer? You just, yeah, but how did you count 3? You summation, yeah? So you sum up. So it's a simple solution. But we don't want to have 2 to the 64-bit arrays. So what the research has been doing is try to have a smaller number of counters and figure out an approximation. So everything I'm going to do from now is an approximate solution. And the protocols or the algorithms are fairly simple, and so I'll present them, but the difficult part is the analysis, assuming what kind of distribution, is it Gaussian, is it Zipfian, and then there is more work, and I'm not going to give you the details of that, but I will give you the results. So the early paper that came out to discuss this was Flageolet and Martin, and it came out in Fox 1983. So this is like 50 years ago, 40 years ago. And it's in Fox, which means it was Fox's Foundations of Computer Science. So this is the most theoretical computer science conference you have, which shows you these problems start very theoretical and then become very practical. So, and the problem nicely, if you look at the abstract, it just says they want to count the different elements. So it's really the perfect problem, the perfect description of the problem we are talking about. So it's probabilistic counting. You're all familiar with hashing, yeah? Hashing, hash functions, okay. So it uses hashes, basically. And we'll assume that we have a hash function that is very uniform. Mathematicians have worked hard on this, and there are good hash functions that are fairly uniform. We are not going to worry about collisions and all the practical problems. So what you do is, my universe had 2 to the 64 possible entries. Every ID that comes, we're going to hash it into 64 bits uniformly. And then I'm going to keep track of the maximum number of trailing zeros. Let me explain this with an example. Let's assume things are coming and they are uniformly hashed into 64 bits. How many of them do you think will end with a 0, and how many will end with a 1? Well, I'm talking binary. Yeah, half. So if I uniformly hash, half of the time I'll have an even number, half of the time I'll have an odd number. And so I'll have 1 trailing 0 half of the time. I'll have 2 trailing zeros a quarter of the time. In general, I'll have 1 divided by 2 to the k of the time, I'll have k trailing zeros. So now what Flageolet and Martin do is they say a user hashes to a string with k trailing zeros with probability 1 divided by 2 to the k. That's the argument we've been making. And so if any hash has k trailing zeros, then the expected size of the set that resulted in this one element that hashed to k trailing zeros is 2 to the k. So that's an expected size, it's probabilistic, and we end up with an approximate solution to the problem. So here's an example. An element comes, it's hashed to this, it has 0 trailing zeros, another one hashes to 12, which has 2 trailing zeros, another one hashes to 8, which is 3 trailing zeros, hashes to 9, 0 trailing zeros, so you don't change the number, you just keep updating it as long as I want to find the biggest one, yeah? So at the end, I have a set like this. What is the number of elements that actually came? I got 6. What is the estimate size that we're going to give? 8, because 2 to the 3 is 8. So the estimate is 8, in reality it's 6, but it is a good approximation. Don't take my word, it's really the math that does this. I'm going to show you the results in the next slide. But basically you keep track of the maximum number of trailing zeros. So the question is, how much space am I using now? So the universe is 2 to the 64. I hash it to 64 bits, but all I need is to track the maximum number of trailing zeros. So I have a pointer in 64. So it's only 6 bits. So it's log. I take log to get 64, and then I take a log of that to get 6 bits. If you think about it, it's 2 to the 64. 2 to the 6 gives you 64, and then 2 to the 64 gives you the big universe number. So in terms of space efficiency, this is very good. It's not as good as constant, but it is as close as you can get without being a constant. I mean, L log star would be better, but we don't get there. Okay? So this is known as the log-log counting algorithm. And it has a lot of nice properties. Most important one is that 2 to the r, 2 to the number of trading zeros, will actually give us a very close number to the distinct number of elements. And the paper has not very difficult proofs for that. And what's more important is there are lots of interesting optimizations. So in particular, instead of using one hash function, I could use different hash functions so that I increase the probability, the possibility that I have real uniformity and taking averages. So there are lots of ideas that have been developed since that have really given very good performance. One important property that I want to alert you to is that this algorithm and all the data streaming algorithms that I will present today have to be linear in terms of time cost. Every element just passes once. Think of it as a network and the packets are coming through and you just have one chance. It's not like sorting. If sorting, you have to do n log n or n square or something more than that. You have to do more than one scan of the data. Here, these are one scan algorithms. So all of them are known as one-pass algorithms, and they are linear. And the memory is very small. And it has many applications. So this is in database context. It's used for query optimization. We are often interested in cardinality estimation. Okay, so this was in terms of background. Getting closer to the problem I'm interested in working on, or we've been working on, is the frequent elements problem. Yeah, come in. Okay, so if you missed what I said, it won't affect it. This is a beginning of a new problem. So, the frequent element is a very popular problem. We are often interested in finding what are the most frequent elements, what are the most popular cities in Kazakhstan, what are the most who visitors come to. You're not interested maybe in every possible visitor to Kazakhstan, every little village they visit. You are going to build hotels, say. So you're going to build it in the top 2, for example, or 3. So often we are interested in top K, top 2, top 1, top K in general. Sometimes it's called the top K problem. Sometimes it's called the heavy hitters, meaning where is the heavy hitting coming in? And it's been around for a long time. The original problem came up as just counting the majority. Who has the majority? So you can think of people voting which is the most popular city in Kazakhstan, and you get the votes streaming in, and you know one of them is going to win. It's either Almaty or Astana, let's say. So there are streams coming in of just Almaty, Astana, Almaty, yeah, just like this. And you want to figure out who has the majority. So this was an old problem that was again proposed in 1981 by 2 guys called Boer and Moore. And how many of you are PhD students here or graduate students? Okay, you've published papers? Have you gotten rejected? Yes. Okay, so here is a story about these 2 guys. So they proposed this algorithm, which I'll describe. It's very simple. In 1981, they sent it for publication, and they were confident it's going to be published. And so they went around the country in the US, and specifically went to Cornell, and gave talks about their work. Another 2 guys, Mishra and Grease, attended their talk, and then figured out they can generalize it. So they generalized it to K instead of majority, and then submitted it for publication, and it got accepted. And then the original authors were given back the referees who said, there's a generalization of your work, we are not going to accept it. So the original work was never published in a referee journal. Eventually it was published in a retirement book that collects papers, a Festschrift later on. So this happens, yeah. but good work eventually is recognized. So what was their solution? They're going to identify who has at least a majority. Yeah? So we know there's only 2 cities that we are competing with. And the algorithm works using just a constant amount of information. You keep track of the ID of a candidate and a number with it. So just two registers. That's all. So it's a constant. It's not a function of the size of n, the number of elements or whatever. So let's say a new element comes, we check, is it similar to what we have or not? At the beginning, there's nothing, or if the value associated with whatever is there is equal to 0, I take the new element and that becomes the candidate. And we give it count 1. If the element that comes is identical to the one we are keeping track of, then I increment the counter by 1. And critically, if the element is not the monitored one, I decrement it by 1. So what you see is you'll get Almaty. So it becomes 2. And then Astana goes down to 1. Astana goes down to 0. Another one, Astana, now it replaces it and gets a count of 1. And now if we stop here, Astana wins. Yeah? So I think it's fairly obvious that it works. What Mishra and Greece did is they generalized it to k elements. So I'm keeping track of k elements instead of just the top 1. I'm now interested in the top 3, in the top 5, in the top k. So I keep track of all the. So let's assume at this point, it's the same idea, just generalize it to 3 elements or k elements. I'm keeping track of 3 elements here. I'm interested in the top k. So I got 6 blue and 4 yellow, and then I got 1 red. There's still an empty slot. I put it in. And then a yellow. I increment the yellow by 1. And now the green comes. The rule is the same like Boer and Moore. You decrease everybody minus 1. So now you decrease the blue, and the red gets kicked out because it's 0 now. And so on. Yeah? So it's a straightforward generalization. So this is the problem we were motivated to work on. And it's basically now it's being called the approximate frequent elements count. And given a stream of n elements, you are interested in finding the top k or the top 1% or some ratio. And there is an error that is going to be associated because I'm not going to keep track of everything. I'm going to keep track of a subset. The problem started in 2003, 2004. My graduate student, Ahmed Mitwalli, he did an internship. This is, remember, the dawn of the internet, advertising in particular. So we had in Santa Barbara, we were lucky, we had a company that was exploring ads. So they basically, if you are a publisher, you publish ads like CNN or BBC or ABC, and you put ads on it, and when somebody clicks on it, then an ad for Coca-Cola, for example, then Coca-Cola needs to pay CNN some amount of money. That's what these companies do. Now, what they are afraid of is that somebody fakes an ad and a publisher, and then puts an ad on a publisher on CNN, for example, and then keeps hitting a lot. And now they're going to ask for money. So that's like a bot master or something. So basically, such bad behavior typically requires a lot of clicks for it to be beneficial. An honest person would not click a lot of times on the same ad. So you're interested in, again, it's a heavy hitters problem. And so he was working at this company, and they were interested in finding out new algorithms for this context where the space is very big. And so that motivated us to work. So you never know when new interesting problems will come. I've had very successful things happen when my students go and work in industry, or my colleague goes and does some work or consulting, and then new ideas, problems come up. So there are lots of products, and you are interested in keeping track of them and figuring out fraud in general. So we developed this algorithm, which I'm going to explain to you briefly, and it's called space saving. And it is, again, a counter base. So we're going to keep a number of counters, but we can't keep too many because there are too many IP addresses. We can't keep all the IP addresses. The user is willing to tolerate some error, and we're going to agree that it is epsilon. Most of these algorithms, including ours, is going to use a space that is 1 divided by epsilon, and that's going to be called M. So I'm going to keep track of M counters. And this paper was very successful. Actually, it won a Test of Time award, so it's been used a lot, this idea, in networking, like I mentioned before. So let's look at the algorithm. Basically, you are going to have an approximation, like I said. So you want to get the top K or 1%, but you are going to get a few more because there's this error. So you're going to get a stream of numbers, and you want to keep track of who is the most popular as much as you can with a good effort. So we have a sum of the frequencies, and you're going to say, I'm interested in a certain percentage. Let me give you the algorithm. So I'm going to keep track of 3 elements again, the top 3. Look at the top 2 lines only for the moment. I'm going to keep track. It's like what Boyer and Moore did at the very beginning. Going to keep track of an element and the count. The error, I'll show you where it comes in. So we are keeping track of 3 elements of the top 3. So we'll get a bunch of elements, a bunch of A's and B's. So up till now, everything is accurate and there's no error. And I got 2 A's, 2 B's, and 1 C. Another A comes, I increment. B comes, I increment B. And now we are going to get a new element, which is D. And the question that all of these algorithms differ in is what to do once the array that's keeping track of elements is full. So what do we do with, so in Greece and Mishra, what did they do if D came in? Does anybody still remember? You subtract from everybody -1. We are going to do a different rule. What we are going to do is we're going to replace the lowest element, C, with the new element, D, and initialize it to the value that C had, that the minimum element had. Okay? So now D is going to be 1, which is inherited from before, because I don't know what happened in the past. That's kind of the intuition. And you give it, so we are going to initialize it to 1. We are going to add 1 to it, so it's 2. And you know, because you know the whole history, that there is a maximum error of 1. So that's the kind of the algorithm. And things go on like this. So if I get a bunch of D's and B's, I increment them. Now if an E comes, you're going to get rid of the D, which was the smallest element, get rid of it, initialize it to 3 plus 1, so it becomes 4, and it goes in there. Okay, so the algorithm is very simple. If an element is being monitored, incremented. If an element is not being monitored, replace the minimum value with the value that was there and just add 1 to it. Everybody kind of understands the algorithm. Okay, and so on. The algorithm has a lot of very interesting properties. I'm going to give you some of them just so that you get an idea, but basically the sum of the counts, because I always add 1 always whenever an element comes. So the sum of these is always the total number of elements that have come. In practice, if you are worried, we typically look at windows. So you reinitialize it. But I'm giving this in a general setting, but it's typically used in. What's more interesting is the minimum element is really less than or equal to all the elements that came divided by, assuming uniform distribution, which is not usually the case, but if it was, then divided by the number of counters that you have, which is divided by n. That's the number of counters, which really is epsilon, which is the error, times the number of elements that I have. So the value 4 really helps me with the bounds. So the minimum number is a bound on the errors. Here, this value must be greater than all of these. So now you can, I'm not going to go into the details, but this is basically the trick that we use in most of the theorems that we develop to prove that it had the performance and the accuracy of what we're doing. What's important is that if an element has high frequency, more than the minimum value, then it is going to be monitored. It has to be there if it has a high frequency. The count of any monitored element is an overestimate. So the error is always, I am overestimating, never underestimating. So if I report an element, maybe it is not a top K, but I will never miss a top K, which is also good because given the top K, given the people I suspect are bad and doing bot analysis and doing clicks fraudulently, I can at least check them offline. But I don't have to look at the entire stream. I'm now looking only at K. So overestimation is a good property of this algorithm. So basically we make use, and it's especially good when data is skewed. It's not a very good algorithm if your data is uniform. Then elements are going to be in and out, and everybody's going to have a lot of error, and it's not going to. But in reality, in most, at least database applications and networking applications, you have often what's called Zipfian distribution. So you are data science people. Yeah, so there's some elements that are very popular. I'm going to show you, I think, here. Here is a Zipfian distribution. These are the highest ranked elements, top 1, top 2, top 3, top 10. They have very high frequency. The probability of seeing them is very high. These elements are not frequent and they are going to be the long tail. Think of it. What is space saving doing? For these top elements, they are going to be on the left-hand side of your monitored elements. They are not, if they are popular, they are just going to stay there and their count is actually going to be fairly accurate. It's the elements that are being replaced at the minimum value that will have errors. So there is most interesting elements are going to be here. The less interesting, if you are really not interested, if you are interested in the top K, are going to be here. And what's more important, it was this graph where blue is the true frequency, red is the red frequency. If you look at the elements that are heavy hitters, the Zipfian top ones, blue is very dominant and there's very little error. Here, the red dominates, but those are the elements that are not frequent elements, so we are less interested in them. So if your application is for data that has Zipfian distribution, this is going to work well with you. And that's what was established, kind of. So this kind of is the foundation of our work. Part of our work, and it had many different applications in lots of different environments. Fast forward almost 20 years to 2022, I had another student, Fuhang, and we started asking, it's true that we have inserts, we have data coming, but real data also has deletions. It's not all inserts. So, for example, you order some things, there are lots of orders, but you also have cancellation of orders. You give grades in a class, and then students ask for a regrade. So there is a modifier. You have a delete and an insert. You are on Instagram or Facebook or whatever your favorite social medium is, and you're friends, and then somebody annoys you, you unfriend them. So there are deletes as well as inserts. So that's been a question that drives a lot of our work, is data in motion. Data is not static, it needs to have updates, but also inserts and deletes. The traditional models are insertion only. For example, what I presented to you, space saving or KLL, there are lots of different algorithms. People had looked at deletions, and it's basically what's called the turnstile model. The turnstile model allows you arbitrary number of deletions for arbitrary number of inserts. So equal opportunity, there are deletes and inserts. And there are two famous sketch algorithms. These are, by the way, not counter-based algorithms, but hash-based algorithms. They are count sketch and count min and count max. What Fuang observed, or what we were observing, and others had done some work in this direction, is to say there is reality an imbalance between inserts and deletes. It is true that we do have I do unfriend some people, but how many people do you unfriend and how many people do you friend? You probably unfriend 2 or 3 every year or so, but most of the time you are making friends. How many regrades? If I have a class of 100 students, maybe I'll have 5 or 6 regrades. So the ratio between inserts and deletes is not the same. Typically, deletes are a lot fewer. And if you look at a lot of data structures, databases, we consider deletes are often a problem. And if you look at it, we often relegate them to say, I will mark something as deleted and then later on do a reorganization. That's typically what happens in like think of I don't know, your favorite data structure, red-black trees. They are much more difficult. A B tree, which is very important in databases. So this observation kind of holds here again. And so what we did is to start to explore how to support deletes in addition to inserts, but in this bounded deletion model. And the basic idea is to say that there's going to be a ratio between the deletes and inserts. And the ratio is governed by a parameter called alpha. So deletes divided by inserts should be less than or equal to alpha minus 1 divided by alpha. So let me try and give you examples. So if alpha is equal to 1, then I have 0, which means that there are no deletions at all. And this gives me the insertion-only model. So it's a generalization of this. If alpha is equal to 2, then I have 1 divided by 2, so it's 50%. So half of the time I'm going to have deletions. So alpha, the bigger the alpha, you'll have more deletions, and you'll play around with this. And we were able to prove that to solve the heavy hitters problem, any algorithm needs at least size proportional to, or big O of, alpha divided by epsilon. Do you remember the size of space saving, which was insertion only? It was 1 divided by epsilon. So this is a generalization. And what's more interesting is it shows you that the bigger the alpha, the more deletions you have, the more space you need. So deletions inherently need more space. So counter-based summaries track 1 divided by epsilon in the insertion-only model. For the linear sketch, which is count sketch and count min, which was designed for the turnstile model, which had arbitrary deletions, it requires 1 divided by epsilon log u, where u is the size of the universe. That's very big. So even if it's log, it's still a big size. I'd like to avoid that. So there is a gap, and most of the counter summaries provide deterministic guarantees, while the sketch summaries provide randomized guarantees, so probabilistic guarantees, randomized. So The question for us was, is there a deterministic algorithm with space budget independent of U and the number N of elements if we assume the bounded deletion? So we changed the model. We took an existing problem, changed the model, and I would argue to a more realistic model, and then we tried to solve the same problem again. And we were able to show it. So we basically were able to come up with an algorithm. And the important thing I'd like to emphasize is deletions are a challenge. I mean, they do require more space. There are very similar properties to what we proved for space saving. We came up with an algorithm, and the algorithm had this property. It satisfies the guarantees only if insertions happen before any deletions. So they were not general. You can't have interleavings of deletions and inserts. And we were contacted by some French researchers who noticed this and told us, and we ended up having a very interesting collaboration with them. So these were people who came out of the blue, and we started working with them because they identified a challenge in our results, but it was actually a very fulfilling collaboration because we ended up with a new paper that ended up exploring families of protocols for interleaved algorithms. And this was presented just last year. So as you see, like the first work started 2004, 2005, and we are still working on related problems. Basically, we come up with different data structures that can be used to estimate this. I think I'm going to skip this. And I want to just pose a couple of questions before we come to the question I'm going to ask. I'm presenting here work on data streaming, but a lot of my current work is actually on privacy issues. Tomorrow I'm giving a talk in the computer science department. Does anybody know about this? No, okay. So I'm giving a talk tomorrow at 2 o'clock. Professor Adnan is here? No. Okay, so at any rate, so that is where a lot of my focus is. And if you are interested in LLMs, I also am interested in private inference in LLMs. So I will touch on that topic tomorrow at 2. And so in the context of space saving, the question was, can we develop a privacy-preserving space-saving algorithm? And I currently have a student who is working on this. The results are not published yet. We are still working on them. But basically, you have clients sending to an untrusted server, and you want the untrusted server to keep track of everything that is happening without knowing the values or the IDs that you are looking at. So I would like to keep track of space saving, but I cannot do it myself, or I don't want to do it myself. I'm going to give it to somebody else, and I don't trust them. So our approach, and this is what I'll talk about a lot more tomorrow, is to use fully homomorphic encryption. If any of you are interested, I'll delve more into this tomorrow about this stuff. But basically, you can do operations, and what we're doing now is doing operations on LLMs, so matrix multiplication, minimization, and stuff like that, in the context of LLMs on encrypted data without revealing anything. So we are trying to do this for space saving now. So how much time do I have now? Okay, so I have a proposal and I want to figure out the majority. So I can give you one of two applications. I can give you both, but one of two applications, one on caching and one on monitoring. Which one is there more interested? Caching, monitor, network. Let's go for the network. So this work came up again. This is Fuang's work, and we were interested in, we collaborated with some networking people. So the last names, they are all networking people. And they came to us and told us, we want to there's a lot of data monitoring that is happening in software-defined networks. So you have gateways, and they have specific hardware that is trying to keep track of lots of things regarding the flow that's happening of the packets in the networks. So a packet comes, it has a source IP, it has a destination IP, workload, etc. You are interested in finding the distribution as well as understanding if there are sites that are congested or not. So there are lots of IP addresses coming from specific entries. And there is a data plane where the data is flowing, and there's the control plane. And in a software-defined network, you're going to use the control plane to adapt, basically, to what's happening. So, to improve traffic routing, you need to look at the distribution of traffic. However, you are also interested in finding out who is causing spikes in your traffic, what is happening. So you are interested in both the general distribution, even the low elements that I was ignoring with space saving, as well as the heavy hitters. You're interested in kind of a more holistic. So this is our one attempt at trying to come up with a data structure or an approach that would solve multiple summary requirements. As you'll see, we end up using multiple summaries, but they are together integrated. So you are using hardware also that has specific constraints. You have multiple stages, typically 10 to 12, 2 to 10. You have small-sized memory. You don't have a lot of space, so you want a very efficient algorithm. So we are interested in basically looking at IP data packets that have information about source and source IP, source port, source destination IP, destination port, and the protocol. You are interested in finding the frequency, and you are finding who is the heavy hitter. So you are interested in two different things. And you are restricted by this data structure, the hardware that you're given at each of these switches. So there has been some work on this field, and this is the related work. What we do is we're going to start by, we're going basically to have three data structures. The first one is keeping track of the cold elements, meaning elements that are not very frequent. For those, I typically don't get a lot of data. So what I'm going to do is we're going to have a bitmap. Just a big bitmap. Actually, it has 2 bits, so it can count 1, 2, and 3. And every time an element comes, we hash it to somebody in one entry in this bitmap. It's not the whole universe. It's smaller than the whole universe, but we have a good uniform hash function, and it's going to go into this bitmap. So for very cold elements that are not very frequent, we are going to keep track of almost exact count of those. As the elements continue, if an element becomes more popular, so we counted 1, we counted 2, and now it came another one, we can't keep track of all of this. So what we're going to do is, if a counter overflows, we push it to a next stage to keep track of what's happening there. And in this case, we're going to keep track of the warm elements using one of the standard approaches, which is count-min, that I had mentioned earlier, our competitors. But it's a sketch, and it's fairly good. Basically, they do hashes on multiple arrays. So this keeps track of elements that are warm in the middle of the distribution. If one of them overflows, we end up pushing it into space saving, which is very good for very heavy hitters, for Zipfian distribution elements, for elements that are very popular. So like this, we have the entire space broken up between multiple data structures. So the bitmap is good for high accurate approximations for things like cardinality, elements that come once or twice. The count-min avoids hash collisions and keeps track of relatively warm elements. And finally, space saving will get the most space. So you end up with a composite data structure that keeps track of all the elements and entire distribution. And we did a fair amount of experiments. So this was actually implemented in the hardware switches by our colleagues. And we had very low error, and the tail distribution was very good, actually. The F-score was very good. We used different data structures, and the results were fairly accurate. I'm not going to give you all the details. I'd like to open the chance for questions. But basically, this is what you try and do, is to come up now with data structures that would be relevant for multiple statistics that you are interested in. So in general, big data needs concise summaries. We've been working on this off and on. It's not my main focus, but every now and then there's an interesting problem that seems to be related and we work on it. It's mainly motivated from very practical problems, but it has very theoretical foundations. There's a lot of analysis that has to go on. There are old applications and new applications. So traditional databases need query optimizers in the database, network monitoring needs it, but also machine learning. Now we are in a phase where we are taking this work and moving on to privacy, and we are exploring that. And the kind of big question is, are there good summaries that can be summaries for everything? And that's, I leave it open. And that could be used in federated learning in different contexts. I think I'm going to stop here and leave some time for questions, yeah?
Thank you very much, Professor.